We're going. Well, all right, y'all. Welcome to Module 10. This is a very important one because it's the last module that I can count to with my two hands. We're talking about population growth. And today we're going to talk about a type of population modeling called logistic growth. And to really make sense of this, I'm going to take us back to linear and exponential for just a quick second. And I want you to recall the way for each of those we would get the population at the next time step. So without knowing what time we're at, what the value of t is, just knowing the previous time steps population, how would we do it? And so I'm just going to put a little recall here. Recall this thing that you obviously remember. For linear, it looked like this. It was p of t, so p of the current time was equal to p of the previous time, t minus 1, plus r times p of 0. So plus r times the original, the starting point. So this is linear growth. There's just, because this never changes. The original population size never changed. So r times p never changes. You're just adding the same amount every time. That's how it worked. And so for exponential, it was slightly different. But only slightly. So for exponential, it was p of t equals, what was it? It was p t minus 1 times 1 plus r. So now it's just getting bigger and bigger, and it gets bigger in a way that's proportional to its size in the previous time step. So this is how you end up with a population that just grows, and the rate at which it grows just continues to increase. It just blows up. So for both of these, it was possible to get a form of the population at any time t, where you plug in t. So for this one, it was, for linear, it was p of t equals p, original p plus p rt, like that. And then for this one, for exponential, it was p of t equals p naught times 1 plus r to the t, something like that. So this was possible for both of these two. And now I want to talk about a different type of growth where it does not just increase or decrease the whole time. So that is going to be called logistic growth, or logistic population dynamics. And the way this works is, at some time t, our population is equal to some rate r, and remember that r has slightly different interpretations for all of these, so don't worry about it too much. Some rate r times p of t minus 1 times 1 minus p of t minus 1. So again, only one parameter here. This is r, so r is like our fertility rate. And this type of model is really useful for thinking on the yearly scale for a population of some sort of animal. You can think frogs or rabbits. Rabbits are a pretty good one because they breed like rabbits. So either way, every year we can get the population, we can get the current population size based on the previous year's population size. And so an interesting thing about this, oh, and another thing that I want to mention is that P of any number is between 0 and 1. So in the previous, so this is important. In the previous examples, we were letting P just be a number of organisms. But in this case, we're treating P as the proportion of the maximum possible population. So we take 1 to be a full population. The population cannot possibly get any bigger than this. And we take 0 to be all the rabbits are dead. So that's important to keep in mind here. Is that P has to be between 0 and 1 now, which was not true for the previous ones. Okay, so the other thing to notice then is that this number P times 1 minus P is going to be, for very small p, it's going to be very small because we'll be multiplying a small number times 1. And for very large p, this number is going to be small because it's almost 1. So p very close to 1 will give you almost 1 times something very, very small. And then this will be the biggest when p is 0.5 because it'll be 0.5 times 0.5, which is interesting. And we'll get more into what that means. But you can think of it like if the population starts off very small, then it just could just get smaller because there's just not enough organisms. Or if P is very large, that means we just have way too many rabbits. They're competing with each other. There's not enough grass. The foxes are having a field day, eating all the rabbits, something like that. And then the population just drops off. So what I'm going to do are a couple examples of how this looks when we pick different values of R, and just kind of see what's going on. So let's go ahead and try R equals, what did I want to try? Let me just check. I believe I wanted to try 2.4 or 2.6. Oh no, 2.3. Okay, so let's try R equals 2.3. And for reasons that we'll get to later, we can't go above 4 here. So we'll try this. And so a good calculator is, or a real calculator, a scientific calculator, is very useful for this type of problem. And I'll show you why in a moment. So let's go ahead and pick a starting population. So let's say P equals 0.5. So this is the population starts at about half of what its maximum could be. So let's just go ahead and plug that all in. So we'll put in 2.3 times 0.5 times 1 minus 0.5. And we get that P1, P after 1 year, is equal to 0.575. And now the important thing about this is that it'll show us what happens over a long period of time. So I'm just going to want to repeat this iteration and see what happens over a long period of time. So I'm going to go ahead and do 2.3 times my answer times 1 minus my answer. So this is just plugging in the previous answer every time. And now I can just keep pressing the button and never type in anything else again, which is my idea of good math. So next we get 0.562, 0.566, 0.565, 0.565, 0.565, 0.565. It seems to be settling on like 0.5652. Either way, you kind of see that we're just getting the same number again after a while. And this is okay. We know, biologists have known for a long time that sometimes populations just stabilize. So I'm going to go ahead and put a graph of what this looks like over here. So R equals 2.3. Let's do time and population, and this one kind of did something like this, and so we'll call this stable. Okay, so the next thing that I want to try is, let's see what happens when we make R kind of low. So we're setting our fertility rate to be something lower than 2.3, and so let's just try like 0.9 for example. And so I'll go ahead and do that. I'm going to set 0.5 again as my starting point. Starting point doesn't matter too much. What matters is what happens over a long period of time. And so now I'll go ahead and plug this in. So 0.5 times answer times 1 minus answer. And what happens? So, wow, the next year, so we started at 0.5, then we got 0.125, looking kind of dismal already. Then we get 0.054, 0.025. Let's wait a few more years. And our rabbits have basically just all died. So, surprise, surprise, with a low fertility rate, like 0.09, or not, like 0.9, I mean, we just get death. So, there's a certain zone for R, this was R equals 0.9. There's a certain zone for R where we get a stable behavior, and then a certain zone for R where we just get a zone of death. But now let's try something else. Let's try making it a little bit bigger than 2.3 and see what happens. So we know that populations sometimes stabilize, sometimes everything dies out if they're just not doing things right. And let's see about 3.2 now, because we want to try to find maybe some more interesting behavior, because population biologists know that sometimes populations of animals just do bizarre things too. Okay, so again, let's put this on here. Again, let's start at 0.5. Oh, whoops. 0.5. And now we're doing 3.2. So 3.2 times answer times 1 minus answer. All right, let's get these rabbits off the ground. So we started at 0.5, and then we got 0.8. Then we got 0.512. We got pretty much 0.8 there, 0.799, 0.512, 0.799, 0.513. We seem to just be oscillating between the same two numbers. So this corresponds to a type of stability in the population dynamics where the population is at one number, and then the following year it's at another number, and then it just switches between those two numbers every year. So this would look something like, you know, kind of interesting. So this would be, so we had stable, death, and then this would be period 2 cycle. So this is a type of stable cycle where this you can think of as a period 1, just stays in the same place, and then period 2 cycle is just flipping back and forth between two things. Fairly interesting. Let's try one more. Let's try 3.4, say. Let's check it out. So T, I'm just going to write R again over here, just to be obnoxious. And starting at 0.05, or at 0.5, 3.4 times answer times 1 minus answer. What do we got? 0.85, 0.4335, 0.849, 0.47, 0.84, 0.44, 0.84, 0.46, and again, we've seemed to arrive at another 2 cycle. So something kind of interesting, I suppose. Okay, so that's cool and all, but I don't really want to plot the same thing again, so let's just try 3.5 and let's see what happens there. So 3.5, 3.5, let's go. So 3.5 is our starting point, then 3.5 times answer times 1 minus answer. Okay, so we immediately go to 0.875, then 0.382, 0.827, 0.5, 0.875, 0.382, 0.827, 0.5, 0.875, 0.383, 0.827. So again, we've arrived at some sort of stability. We're seeing the same numbers again, but this time it's not period 1, it's not period 2, it's actually period 4. So we're cycling between 0.383, 0.827, 0.5, and 0.875. So this, I suppose, kind of looks something like this. We go, and then it was 0.5. And so on. So this is the period 4 cycle. So that's great. I want to show you kind of a visual way to represent what's going on here besides just punching numbers into the calculator now. So I'm going to show you how to deal with this sort of iterative map. This is sometimes called the logistic map, and there are other types of iterative maps as well. I'm going to show you how to deal with this kind of more visually. So I'm going to erase these graphs now, and we're going to just make one kind of bigger graph. So okay, and instead of time being on one of these axes, we're going to have the previous population, p of t minus 1, and p of t here. So this is literally a graph of this function here. We're graphing the time as a function, or the population at one time as a function of its previous time. And this, as you can imagine, if you were to FOIL this out, you would get r times, and then in parentheses, p minus p squared. So this is a quadratic, but it's a flipped quadratic because the squared term would be negative. So we're going to get something kind of like this, where this point is 1, and of course this is 0, because you can see right from here that our values are 0 when p is either 1 or 0. So this is kind of what it looks like. And then the next thing that you do is you go ahead, and we should put 1 here as well. You go ahead and draw the y equals x axis. So this would be p of t equals p of t. So this is equivalent to like y equals x. You just draw the line with slope, a line with slope 1 right here. And the way this works, if you want to iterate, is you start on, so we started at 0.5, and this corresponds, of course, to r, not of course, this corresponds to r equals 0.9. So if you were to plug in this into your graphing calculator with r equals 0.9, you would get something like this, and then if you plotted the line with slope 1, you'd get that. And so we started with, in our example, at population equals 0.5. And so the way this would work visually is you'd start at that point on the straight line, and then you'd draw a vertical line to the plot, or to the parabola. Okay, great. Now the next piece is to draw a horizontal line back to the y equals x. So do that, you end up here. Now repeat the process. Go down, well, down or up, vertical line to the parabola, horizontal line to y equals x. Vertical line, horizontal line, vertical line, horizontal line. Eventually, it's getting too small for me to draw, but we're just approaching 0, and this thing would just bounce back and forth. This is what's called a cobweb plot. And it's basically the visual representation of these types of iterative maps. So that's great, but let's look at maybe our more interesting example. So I'm going to try to erase this without erasing too much. So let's go ahead and plot it with r equals 2.3, that first number that we tried. So that would look something like this. And my drawing's not perfect, and kind of the downside to this is that it helps the accuracy if you draw a good parabola. But this should work nonetheless. So again, we're going to go ahead and try, we're going to try 0.5 as a starting point. So I'll put here. And remember, what happened was we went vertical line to the parabola. So let's do vertical line to the parabola, and then horizontal line to the function, and then vertical line to the parabola, horizontal line to the function, and we're just going to end up on this fixed point. And it's the same fixed point that we had before. Interestingly enough, if we were to start at a different value for the population, let's say we started at like 0.1, then we'd go up, over, vertical, horizontal, vertical, horizontal, and we'd get there nonetheless. Similarly, if we started with a population of like 0.9, that would be here. We'd go vertical, horizontal, vertical, horizontal, and then we're back at our fixed point. So no matter where you start, you just end up back at this fixed point. So this fertility rate, this shows how this fertility rate will end up with a stable population size. Okay, great. So how about now we try the 3.2 now. So we've got our y equals x, and now 3.2 would look more like this. It would be up, and then coming down, I'm going to try to kind of sketch this so that it comes out about right. Not the best parabola, but we're working with it. Okay, now let's go ahead and try this cobweb process. So starting around 0.0 or at 0.5, vertical, horizontal, vertical, horizontal, vertical, horizontal. And the important thing to be paying attention to is where we're landing when we go back to the y equals x axis. This corresponds to our 2-cycle stability, and you can see that every time we repeat this process, we're just going back to the same points. And it would end up this way regardless of where we start, as long as it's between 0 and 1. So starting here, we go, and then we're there again. Or maybe here we go. So this is the type of complex behavior that we can get from a very simple equation with only one parameter. So we're going to explore more of this on Thursday. I will not be in, but I'll have a substitute who knows a lot about this stuff, and he'll be able to guide you through the process. And you'll discover a lot of new great things involving this logistic pattern. This is mostly just an intro of the way to think about these things, but it's really going to take some, it's going to take a healthy amount of suffering to really start to see what's going on here. So thank you for bearing with me, and I will see you when I'm back on Tuesday.